So once you know what the moment of inertia is, how do you determine it for different kinds of objects? Well, the good news is we are not in this class going to attempt to learn how to actually determine the moment of inertia for different shapes of objects. This is a little bit mathematically difficult. So what we're going to do instead is I have this table of pre-calculated moments of inertia for some of the common shapes that you'll encounter in problems and in everyday life. You'll find a similar table in any textbook. You'll find a similar textbook, a similar table if you Google this or look on Wikipedia or whatever. So here are some of the ones that I think are the most important. You've got a cylinder. So this would be like you have an object that's cylindrical like this, and you rotate it about the center of the cylinder. So like imagine, like for instance, you roll this cylinder across a surface and it's rotating along the length of the cylinder. So if you have that situation, the moment of inertia is, and the formula is given over on the other side here. So the formula there is 1/2 times the mass of the cylinder times the radius of the cylinder squared. Why 1/2? Well, that's the part I can't explain to you. That's the part that requires a lot of calculation to figure out. One thing I can tell you about understanding where these fractions are coming from is that the moment of inertia is generally higher if the mass gets further from the axis of rotation. So for instance, if you compare these two, the solid cylinder and the hollow cylinder, you'll notice the solid cylinder has a lower moment of inertia. The hollow cylinder moment of inertia is double compared to the solid cylinder. That's because in a solid cylinder, the mass is all distributed throughout. For a hollow cylinder, it's all at the very edge. So putting all the mass at the very edge is going to lead to a really high moment of inertia. For the solid cylinder, you can actually, in this case, even understand why it's 1/2, because the mass is like evenly distributed throughout. So on average, the mass is about halfway out. So as a result, the moment of inertia is about half. You know, I mean, this is a very sloppy argument, but you can at least kind of wrap your head around why it might be in the ballpark of 1/2. We've got then a similar thing down here for spheres. We've got a solid sphere versus a hollow sphere. By the way, 2/5 is 0.4, remember? And 2/3, that's 0.67. So once again, you'll notice the hollow sphere is higher moment of inertia compared to the solid sphere for exactly the same reason as before. Then we've got thin rod. The thin rod one means this example we were talking about, where you take something long and thin like this, and you hold it at the center of mass. You hold it at the center point, and you spin it like that way. Spin it this way, so that the axis of rotation is passing through the center like that. And in that case, it's 1/12 times the mass times the length square. One small thing to make note of in this formula that sometimes people mess up, notice that in this one, it's the entire length of the rod that goes in. It's not the radius of the rotation, because the radius of the rotation is actually only half the length. Because if you think about it, if you picture this circle like this, the radius is actually of the circle is actually just like this, but you use the entire length in that formula. And then lastly, one I like to include in my table personally is just to remind me that the point mass has 0 moment of inertia. A point mass means that all the mass is concentrated to a single point. And so that object basically has no size and shape. Since it has no size and shape, it has no moment of inertia, because all the mass is going to be concentrated right at the axis of rotation. So it's going to have the lowest possible moment of inertia. So that is, you know, as far as we're going to go for the most part of figuring out moment of inertia, is just take the shape that you're working with, match it up to this table, and look up what that moment of inertia is. And you should also understand this conceptual idea of like if you compare two shapes to each other, you can see why one of them has a higher and lower moment of inertia, because you're thinking about where is the mass located on the object, and that's going to determine, you know, how the moment of inertia kind of ranks.